So, today we will talk about the second fundamental form of a surface. Second fundamental form on a surface. So, there are two important differential forms. One is the first fundamental form and the other is the second fundamental form. The first fundamental form tells you how to move on a surface, and the second fundamental form gives you the idea of bentness of the surface, how to measure the bentness of the surface. These are the two main invariant of a surface. So, how to measure it? So, what we do, we start with a surface sigma. Say its parametric equation is as usual r equal to r of u1 u2. I will assume that it is a regular surface of at least class C2, and P, choose a point P on it. Say this is r u1 u2. I have chosen a arbitrary point on the surface. So, what we will be doing to this surface in order to get hold of its curvedness or bentness. Suppose I want to see the bentness of the surface at a point P. So, we will draw a tangent plane at P, and I will choose a neighboring point Q on the surface, and then I will drop a perpendicular from Q onto the tangent plane. Now, if the bentness over here is more, this distance will be more. If this distance is small, the bentness will be smaller. So, in fact, the measure of this distance will give you the idea of the bentness of the surface around the point P. So, now how to get hold of this distance d? So, what I am doing? So, I am considering a tangent plane at the point P, and this tangent plane is defined by the equation r minus r. Suppose this point is okay, and dot n equal to 0, where n is the unit normal to the surface, where n is as usual is unit normal to the surface at the point P. That is, n is equal to r1 cross r2 upon modulus of r1 cross r2. r1, r2 are known to us, they are the basic tangent vector on the surface. r1 is the derivative of r with respect to u1, r2 is the derivative of r with respect to u2. So, this is the normal to the surface. Now, look what we will be doing. Let me join these points P and Q from the origin of my coordinate frame. If I join the point P and Q, then this P Q is a vector. What I will do, and now draw the normal n also. This is suppose the unit normal n. If you want to draw the same normal from the point Q, it will go like this. Okay. Now, what you do, you just drop you just think of the projection of P Q onto n. Look at the projection. So, consider the projection of P Q onto the normal n. You can physically see that if I drop a perpendicular from P onto the normal n, then this distance is actually d. So, in fact, d is nothing but the projection of P Q onto n, that is projection of p q onto n. And this p q vector is how much? P q vector you can see from the figure. If point q is a neighboring point, let me write down over here, and q is something r of u 1 plus something h 1 u 2 plus h 2. This is a neighboring point of P on the surface, of course. Okay. So, now you can see what will be the vector P q. It will be r of u 1 plus h 1 u 2 plus h 2 minus r of u 1 u 2. This is the vector P q. Now, you consider its dot product with n, that will be in fact d. So, d is this much. Now, if you want to see it in terms of the derivative of r, since we have assumed our surface to be regular, you can find an expansion of r of u 1 plus h 1 u 2 plus h 2. So, by Taylor series, we have r of u 1 plus h 1 u 2 plus h 2 equal to r of u 1 u 2 plus r 1 or h 1. So, you write down something h 1 into r 1 of u 1 u 2 plus h 2 r 2 at the point u 1 u 2 plus higher order derivative. Let me write down r I j. Okay. I will tell you what r I j is, into h I h j 1 upon factorial 2 plus more terms. I will say they are the terms of the order of h 1 is square plus h 2 is square. Okay. Okay. So, plus terms of the order of plus terms of the order of h 1 is square plus h 2 is square, h 2 is square. Okay. So, this is the Taylor series, or I can rewrite it as r of u 1 plus h 1 u 2 plus h 2 minus r of u 1 u 2 equal to, I can combine them, these two terms, and that can be written as some r I u 1 u 2 into h I, okay, plus half of r I j into h I h j plus terms of the order of h 1 is square plus h 2 is square. Okay. What is r I j? Where r I you already know, where r I means del r over del u I. R I j means del r I upon del u j. Okay. Yes. Second, or you can also write it down as delta 2 r upon del u I del u j. This is what we mean by r I j. These are the symbols that we will be using all along. So, you need to remember the symbols also. Okay. Now, let me rewrite down this series. So, next we will take the dot product with n in both sides. So, taking dot product with n in both sides, the above equation will become u2 plus h2 minus r of u1 u2 dot n. In the right side also you will be having r I u1 u2 dot n into h I plus half r I j dot n into h I h j plus terms of the order of h 1 square plus h 2 square. Okay. Now, the left hand side is d. So, or d equal to, now this term will go off because r I is a tangent vector, derivative of r with respect to ith parameter will be a tangent vector. So, the dot product of tangent and normal will always be 0. So, what are you left is only half of r I j dot n into h I h j plus terms of the order of h 1 square plus h 2 square. So, I will not care much about these terms because they are tending towards 0 quite fast. Okay. So, d is for all practical purposes depends on this quantity. So, let us go get hold of this quantity. So, let us denote this quantity r I j dot n by a symbol b I j. It depends on the indices I and j. So, this is the notation. So, denote r I j dot n by the symbol b I j. So, what we see is that the bentness is basically depending on these quantities b I j's, or geometrically speaking the deviation of the surface from the tangent plane depends on the projection of the second order derivative of r onto n. So, we must concentrate on these quantities. These quantities seem to be responsible in telling you the deviation of the surface from the tangent plane. In other words, it gives you the measure of bentness of the surface. Okay. So, what we are going to do next? We are going to construct a differential form, a quadratic form taking b I j's as the coefficients. So, consider a quadratic differential form I will denote this differential form by the symbol second. We will do it, you see I and j varies from 1 to 2. So, how many symbols you will be having? 4 symbols B11, B12, B21 and B22. Okay. So, this I will write down as Bij into dui duj. Okay. Or if you want to write down in the expanded notation. So, I and j are dummy indices. So, when you will expand it, it will be B11 into du1 square. One thing you can notice over here itself that Bij is symmetric in I and j. So, that is an immediate observation over here. The observation is that Bij is same as Bji, okay, because Bij is Rij dot n, Rij means derivative of r, second order derivative of r with respect to ui and uj, second order derivative commute. So, Rij is same as Rji and therefore, Bij is same as Bji. So, you make yes, yes. We have in the beginning written down that the surface is smooth. Okay, that's right. That's right. And in particular, B12 in particular, B12 is same as B21, because all other entries are B11, B22. So, symmetry does not play much role over there. So, now I was expanding this summation. So, B12 du1 du2 plus B21 du2 du1. So, you can combine them 2 times B12 du1 du2 plus B22 du2 whole square. So, this quadratic form is called the second fundamental form. This is in the compact notation, this is in the expanded notation. So, this quadratic form is called second fundamental form. Or in short, we can also write down S dot f of the surface. One thing you can understand by yourself, that all these first fundamental form and second fundamental form, they are basically defined at the point P. Okay. When you will move to some other point of the surface, deviation may change, and therefore, these quantities B11, B12, B22 will be should be regarded as function, whose value at a point will be scalar d, but at other point it will be some other scalar and so on. So, you can globally consider Bij's as functions on the surface. All right. So, these are second fundamental form, and these B11, B12 and Bij's are called the coefficients, coefficient of second fundamental form. Now, we will look into some of the properties of Bij's. So, the first observation is, you can make a matrix out of these coefficients. So, the matrix of the coefficient is a 2 by 2 matrix of coefficient of, yes, in the same manner, on the same lines. I will denote this by symbol Bij, and actually it is this matrix B11, B12, B21, B22. You can write this also as B12, because both of them are same, and determinant of Bij will be this determinant B11, B12, B12 or B21 and B22. When you will expand it, it will be B11, B22 minus B12 square. All right. Now, some more important relation, they may be useful to you. So, consider, we know that n is perpendicular to both the basic tangent vectors. This dot product will be 0 for I equal to 1 as well as for I equal to 2. Now, if I differentiate this relation, so differentiating this relation, will give you, when you differentiate partially, because it is a function of two variables. So, let me differentiate with respect to jth parameter. Okay. So, it is derivative of n, that is n j dot r I plus n dot derivative of r I with respect to u j is this. Okay, right side is 0, after differentiation it will remain 0. So, what you get, this quantity is b I j. So, b I j from the above relation is equal to minus times r I dot n j, and as b I j is symmetric in I and j, as you have noticed earlier, this is same as minus times r j dot n I. So, one can write down this as a definition of b I j sometimes. Okay. Okay. There is another important observation here. Look at this. So, consider d n dot d r, total derivative of n dot total derivative of r, because n is also moving on the surface. Whenever you have a surface and you take at every point the normal, it will go on changing its direction. So, it is a variable, okay, a function of the u1 u2 both. So, dn means del n over del ui into dui. So, this will be what? dn, if you want to see what it is n1 into du1 plus n2 into du2. n1 means del n over del u1, n2 means derivative of n with respect to u2. So, this is how we choose our symbols. So, in short, this is n I dui. So, this is n I dui dot, this is r j duj. So, the dot product of n I and r j multiplied by dui duj. n I dot r j you have just seen is minus b I j. So, this is minus times b I j dui duj, and throughout I and j are dummy indices. So, the right side is actually minus times the second fundamental form. So, the second fundamental form can also be written as the dot product of dn and dr. So, this is also an important relation which we should keep in mind, that second fundamental form can also be written as minus times dn dot dr. Yes, direction. Now, this right side is a scalar quantity. So, if you are writing the quadratic form, means it is a negative term. Okay. Depending whether dn is negative or positive, I can't say, but it is a thing that appears in the computation. Okay. All right. Next, G and B I J? Yes, sir. G that G sir for first fundamental. Okay. One calculation we can do also by taking sir R I J is equal to R I dot R J. Okay, that we will be doing when we will consider the Gaussian curvature. Okay, we will do it there itself. Now let me take up some. So that half of this G is equal to half of Good. Pick up some problems based on the coefficient of second fundamental form and this. So, some simple examples on second fundamental form. Number 1, these are some examples. Show that the necessary and sufficient condition, show that the necessary and sufficient condition for a surface to be a plane is that its second fundamental form is identically 0. Okay. The trivial case for a curve to be a line was that its curvature is 0. Now, the curvature means the second fundamental form. So, in case of a surface, so this must be 0. Number 2, show that for a sphere of radius a, the first fundamental form ds square is a times the second fundamental form. Number 3, find the second fundamental form for the surface of revolution. Find the second fundamental form for a surface of revolution. Number 4, find the first and second fundamental form, find the first and second fundamental form for the surface z equal to f x y. So, these are some simple exercises on the second fundamental form. Okay. So, let us solve these exercises. I will just give you a hint of these problems. Look at the first one. Show that the necessary and sufficient condition for a surface to be a plane is that its second fundamental form is 0. If you look at the plane as a surface, then you will notice that a surface is in Cartesian coordinate, it is a x plus b y plus c z equal to some constant d. Okay. Or you can say z equal to a x plus b y minus some constant d. You can divide by c and things will be like that. Okay. So, z is a function of linear function of x and y, and this d, what it is doing? It is just translating the plane. It is not changing the geometry of the plane. If I take d equal to 0, the plane will pass through the origin, otherwise it will pass through some other point in the space. Okay. So, no need of considering the constant all the time, it is immaterial. Okay. So, the equation of a plane is in Cartesian coordinate looks like this. So, I want the parametric equation. So, the parametric equation, of a plane passing through origin, passing through region is given by x you can take as u1, y you can take as u2, and z you can take as au1 plus bu2. So, this observation suggests that this is the parametric representation of a surface. Okay. So, if you want to write down the position vector of a point on a plane, it will be u1 u2, or if you want to take x y, okay, x y and ax plus by. Okay. Here x and y are the parameters of the regular surface plane. Okay. Now, R1 means 1 0 a, R2 means 0 1 b. Now, 1 and a b are constants. So, the second order derivative will vanish. R11 will be 0, R12 will be 0, R22 will be 0. So, Rij is 0. So, it is immediate to observe from here that Rij is a 0 vector, and therefore, Bij must be 0. So, from here you can see that Bij is also 0. Once the coefficient of second fundamental form are 0, the second fundamental form is identically 0 for a plane. Okay. So, this is how we can prove the direct part. The other way around is also simple, you can go the other way. Okay. Yes, that means it is a plane, that is same as tangent plane of the surface. Okay. So, that was obvious. Now, move to the second problem. In the second problem, we have to work out the first fundamental form and second fundamental form both for a sphere of radius a. Now, if you remember, the parametric equation of a sphere is written as a cos theta cos phi, a cos theta, y is, it depends what angle phi and theta you are choosing, y equal to a cos theta sin phi, and z is a sin theta. Okay. These are spherical coordinates. So, this is how this becomes a parametric equation of the sphere with theta phi are the two parameters. Okay. So, the position vector of a point on a sphere will be a cos theta cos phi, a cos theta sin phi, and a sin theta. And R1 means derivative with respect to theta, that will be minus a sin theta cos phi minus a sin theta sin phi, and this is a cos theta. R2 will be equal to derivative with respect to phi, means minus a cos theta sin phi, and this is a cos theta cos phi, and this is 0. R11. So, now this you have to differentiate with respect to theta. So, this is minus a cos theta cos phi minus a cos theta sin phi, and this is minus a sin theta. R12 you can also write down. So, this is derivative of R1 with respect to phi. So, that is a sin theta sin phi, and this is minus a sin theta cos phi, and this is 0. Okay. And R22 also we can compute. So, you have to differentiate R2 with respect to phi. So, this is minus a cos theta cos phi, and minus once again a cos theta sin phi, and 0. So, these are Rij's. These are Rij's. Okay. Now, you have to compute Bij. So, for Bij I need R1 cross R2. So, R1 cross R2 I can compute directly from here. This is R1, this is R2. So, R1 cross R2 can be computed. That can be done by determinant I, j, k. R1 is minus a sin theta cos phi minus a sin theta sin phi and a cos theta. R2 is minus a cos theta sin phi a cos theta cos phi 0. This is how much? 0. So, minus a square cos square theta cos phi, then minus this is 0, and this will become a square cos square theta sin phi. Okay. Then minus a sin theta cos square phi, and this will be, okay, let me write down, minus a square cos theta sin theta cos square phi. Okay. Then minus, and then minus, okay, minus once again a square cos theta sin theta into sin square phi. Okay, a square you can take out. So, this is okay. Minus also you can take common. So, this is cos square theta cos phi, and this is cos square theta sin phi. So, this cos theta sin theta you can take common, cos theta sin theta take common, and that will give you cos square phi plus sin square phi, which is 1. So, that is this is R1 cross R2. When you will take its mod, see what will be the mod. Okay. How much will you? This square plus this square means cos 4 theta into cos square phi plus cos 4 theta into sin square phi plus cos square theta sin square theta. So, cos 4 theta common. So, this will become just 1 plus cos square theta sin square theta. So, cos square theta is common. So, this is just 1. So, mod is mod of R1 cross R2 is nothing but a square. So, this is just a. No, this is in fact mod a square. Square. Okay. This is mod of R1 cross R2 square. We have taken dot product with itself. So, this is mod square. So, this will become A cos theta. Okay. Now, when you will divide this by A cos theta, no, this is R1 cross R2, I am sorry, this is R1 cross R2, I am sorry, this is mod of R1 cross R2 square. So, this is mod of R1 cross R2 square. A square I have forgotten to write. So, A square was there, in fact, A to the power 4 was there. So, A to the power 4 was there. So, A to the power 4 I forget to mention. So, that is there. So, this is A square cos theta. Okay. So, when you will divide this by A square cos theta, you can get n. So, from here n comes out to be, which is R1 cross R2 upon modulus of R1 cross R2, that is, this has to be divided by A square. So, this will go, and cos theta means just cos theta. So, this is simply cos theta cos phi, and here you will be getting cos theta sin phi, cos theta sin phi, and that is sin theta, and this is what we were expecting also. This is the unit normal with minus sign, you are right. In fact, this is the position vector, opposite direction position vector. So, you know it on the sphere. In fact, we should have written it directly. If this is the sphere, then the tangent, then the normal of this will be actually this vector, and if you go in the opposite direction, that will be the radius vector. Okay. So, that is why you are observing that the radius vector and the normal vector are just opposite to each other, and its magnitude should be 1. So, magnitude is 1. Okay. So, this is the normal. So, everything is in our hand. Now, we have to write down the second and first fundamental form. So, first fundamental form first. So, ds square, this is the first fundamental form, f f f. It must be G11, G11, okay. You can see from here what is G11, we can compute directly. This is R1 dot R1, sorry R1. So, this is A square sin square theta cos square phi, A square sin square theta sin square phi, A square sin square theta I will take common, plus A square cos square theta. So, it is simply A square. So, this is simply A square. G12, sometime we had computed it is 0. You can see it. This means A square cos theta sin theta cos phi sin phi, and this A square sin theta cos theta sin phi cos phi, they will cancel each other. Here it is 0. So, this is 0. G22, you can immediately see from here, A square cos square theta sin square phi, A square cos square theta cos square phi, A square cos square theta is common. So, sin square phi plus cos square phi is 1. So, this is simply A square cos square theta. So, this is A square cos square theta. Okay. So, ds square is G11 into d theta square plus 2 times G12 d theta d phi plus G22 into d phi square G12 is 0, so middle term goes off. G11 is simply a square into d theta square plus G22 is a square cos square theta into d phi square. So, this comes out to be a square out d theta square plus cos square theta into d phi square. This is the first fundamental form on a sphere, first fundamental form. Okay. Now, come to second fundamental form. So, B11 means, so I need to compute the coefficients of second fundamental form. These are Bij's. So, first B11. So, this is R11 dot n. Where is n? N is there. So, when you will take the dot product of R11, so that will be a times cos square theta cos square phi. Okay. So, and minus from here also I can bring out, if you wish, I can bring this minus out, and there is a minus over there. So, this minus goes off. So, you have cos square theta cos square phi plus cos theta. Okay, let me write down a cos square theta cos square phi plus a into cos square theta sin square phi, cos square theta into sin square phi plus a into sin square theta. So, from here a cos square theta is common, cos square phi plus sin square phi, a cos square theta plus a sin square theta means simply a. So, B11 is simply a. Now, look at B12. B12 means R12 dot n. So, this is R12 dot n. This was R11 dot n. So, R11 2 dot n a sin theta. So, that will become, here also you have to take care of minus. So, this is minus a sin theta cos theta, a sin theta cos theta sin phi cos phi, cos phi sin phi. Okay. And here also minus minus plus a sin theta cos phi sin phi, both will be cancelled out with each other, and the last term is already 0. So, this is also 0. Okay. Then B22 dot B22 equal to R22 dot n. So, R22 dot n. So, you can see from here minus minus plus a cos square theta cos square phi, then minus minus plus once again. Okay. A cos square theta sin square phi. That is all. So, this is a cos square theta cos square phi plus sin square phi. So, all Bij's are also in our hand. Now, we can write down straight away the second fundamental form. As the second fundamental form is equal to B11, which is a into d theta square. B12 is 0 plus B22 is a cos square theta d phi square. So, this is a times d theta square plus cos square theta into d phi square. Now, you see what is the relationship between first fundamental form and second fundamental form. So, you can see that the first fundamental form is A times the second fundamental form. So, it follows from the two box relation that d s square equal to A times the second fundamental form. Okay. So, we should stop at this point and we will continue after break of 5 minutes.